All right, we're rolling along here today. So the topic, I was trying to upload a picture that would show you what it is, but I couldn't really get it to work, and I said, well, I could spend a bunch more time, or I can just talk about differentiability. Differentiability, that's the topic that we're talking about for today. So let's get rolling. So here's what's going on. First of all, we're going to do one more problem with the definition of the derivative, just to get all those pieces into place. One more sort of example that we haven't gotten to so far. And so the problem we're going to try to find out is what's the derivative of y equals the square root of x. So find dy dx, which is the derivative, right? Okay, which is also known as the instantaneous rate of change, and it's also known as the slope of the tangent line, right? So whenever we say any of those things, we're saying all of those things. Derivative, instantaneous rate of change, slope of the tangent line, dy dx, all the little notation. Definition of the derivative, that's that limit thing, the limit of f of x plus delta x minus f of x all over delta x as delta x goes to 0. So here we go. Let's roll with it. So there's my function. We're just going to plug my function into this little formula. I'm going to try to do this. Hopefully I'll leave you enough space to get this all in one swoop. The limit as delta x goes to 0. The f of x plus delta x, that's just the square root of x plus delta x minus my original function, the square root of x, all over delta x. If we run and plug delta x goes to 0 in there, we're going to get 0 over 0, which is the indeterminate form, which means we have more work to do. So let's do it. Here's what we're going to use. We're going to use our good friend, the conjugate. The conjugate, x plus delta x plus that. Multiplying by 1, x plus delta x plus root x. Okay? So, to do that, we're going to do the multiplication thing. We're going to end up with x. So the square root of x plus delta x times the square root of x plus delta x is still x plus delta x. Oops, let's write the limit just to be proper and good. Alright, so we've got x plus delta x. Remember, my inside, my outside balance each other off, neutralize each other, whatever way you want to say it. And then I'm just left with the last, which is the square root of x times the square root of x, which is just x, and it's plus times a minus, positive times a negative, so there. On the bottom, I've got delta x times my conjugate, multiplied by my conjugate. Boom, boom. Okay? X plus delta x minus x is just delta x. Still taking the limit as delta x goes to 0. That's what that says. Over delta x times the square root of some people, and he would be very upset if I didn't close that last parenthesis, Annie Trier. Here, she gets a shout out. So, we have that, right? Boom. Cancel away. Remembering, of course, that we must, a fancy pen, have a 1 up top, right? So it's 1 over. Back to the not so fancy pen. So 1 over that. I can extend the page. Alright, so I get 1 over all of that. And now I can take the limit as delta x goes to 0 of 1 over the square root of x plus delta x plus another square root of x. When delta x goes to 0, this is just the square root of x. This is the square root of x. How many square roots of x do I have? I have 2 square roots of x. Got a 1 on the top. Thus, this is the derivative right here, the instantaneous rate of change, whatever you want to call it, of that. Oh, it all fit on one page. Neat. I was trying to scroll up, but it didn't work. All right, so that's the derivative of that using our friend the conjugate, and we're off. So we'll work a few of those just to keep you more practice. So now to the actual topic of today, differentiability. Differentiability is the ability of a function to have its derivative taken. You can read that. Okay, right out of the word ability, differentiate. Okay, the ability to have the derivative taken. The question is, can we find the derivative at every function of every point? Let's look at a couple of functions. Here's one. Hey, there it is, my friend, the change color scheme button. Don't know why that comes up. Should find out. never think about it till right now. But anyway, this function right here, in order for the derivative of the function to exist, the one-sided derivatives must be equal, must exist and be equal. So if I look at this particular function here, remember the derivative is the slope of the tangent line? So just looking at this, what's the slope going this way as I approach -2? Because that's the point where I'm really interested in, just to give you a little foreshadowing. As I approach -2 on this particular little function, it looks like I've got a negative derivative, right? Negative slope. As I approach from this direction, it looks like I've got a positive slope, right? So if on one side I've got a negative slope, negative derivative, the other side I've got a positive slope, a positive derivative, okay, is it possible that right here, that those two derivatives could be equal? A negative number and a positive number? I think not. Okay, they do exist, but they're not equal in this case. So what we look for when we're talking about differentiability, one thing that's going to give us the heads up is no sharp turns. If we have a function that's got sharp turns in it, we're not going to be able to take the derivative at that particular point. Okay? So we're going to kind of look at places where the derivative we know won't exist. All right, right here, this function x to the 1/3 power, which is just the cube root of x. Okay, what's going on right in this particular little area right here, right there? Okay, it's looking like I'm getting pretty horizontal or pretty vertical at that particular moment. You know, if I zoomed in on this, it would get right as we get close to 0. I'd get almost an infinite sort of slope. Okay, so much we'd say that there's no slope. So much that we'd say that this is a vertical line right here. There, okay. And so if I can't, you know, back to the must exist and be equal, well, the slope and infinite slope doesn't really exist. So one thing we look for whether a function's not differentiable is if we have a vertical tangent. So if you see a function and it looks like it's going vertical at some point, then that would be a case where we'd have some differentiability issues. And like with domain and range and continuity, we're looking for trouble spots more than anything else. Okay. So let's discuss the differentiability of this function. Okay. So as we move along here, would we be able to? Are there places where you'd say, "Oh, got a problem"? Okay. One place you're paying attention, right there. Here's a different color. All right. Right there, sharp turn. Agree? I think so. Again, a place where, you know, in this way I've got a negative slope, that way I've got a positive slope. So right here we're gonna have an issue. Okay. Any place else where we would not be able to take the derivative? And I was gonna say, I'm gonna go to my little cheaty notes here so that we get all the places. Okay. So we can't have any sharp terms. Can't have vertical tangents. I don't see any vertical tangents in there unless maybe we could say it's right there, possibly. So we'd have a vertical tangent, maybe there. Certainly if we have a hole, we can't take the derivative, so there. So if we have sharp turns, vertical tangents, gaps, breaks, anything that's kind of funky looking, that's a place where we're not going to be able to take the derivative of that particular function. Is that right? Okay. Here's my basic rules for differentiability. It's a rule, actually. Oh, what happened there? Hey. Okay, differentiability implies continuity, but not the reverse. So that means if a function is differentiable, it is continuous. Okay? So all differentiable functions, are continuous. Hey, Miss Welch, what's going on? It's all right. Let me pause for a second. All right, that was Miss Welch checking in for a second. So all differentiable functions are continuous. I'm sure I spelled that wrong. Continuous. But it doesn't mean that all continuous functions are differentiable. That's the vice versa part, okay? So not all continuous functions are differentiable. I should just spell it. I should type this up. Differentiable. There you go. Okay. So if we know it's differentiable, we know it must be continuous. But just because it's continuous doesn't mean it's differentiable, because if you look back, That certainly is a continuous function, but it certainly is not differentiable everywhere. Same thing there, not differentiable everywhere, but certainly continuous. Okay, so there's that differentiability implies continuity, but not vice versa. So, oops, that's what we're going to work on tomorrow, I think. It'll be slightly revised. So that's differentiability. Big thing. No sharp turns, no vertical tangents, no gaps, no breaks, anything like that. That's when we're talking about differentiability. We're sort of looking at where it's not differentiable. Okie dokie? I think that hopefully makes some sense. We'll talk about it tomorrow if you have questions. That's about it. Hope you learned something. See you tomorrow.